Hello, welcome to the short lecture on basics of probability theory. So let us look at some definitions. Outcome. An outcome is defined as an output of interest from an experiment. It's basically an interesting result from a predefined from an experiment. Now, next one is sample space. Next definition is sample space. A sample space is basically a set of all possible outcomes without any repetitions or unions. That is, basically it does not have any combinations of outcomes. It basically consists of only simplest possible outcomes. And then event. An event is a set of outcomes that actually satisfy a certain property. An event is a set of possible outcomes that satisfy a particular property. An event space is same thing to events as a sample space to outcomes. That is, an event space is a set of all events that satisfy a particular property, and these sets of events these events are mutually exclusive. So let us look at some examples of outcomes. In order to define an outcome, first we need to have an experiment. That is, a primary requirement for defining an outcome is a well-defined experiment. For example, we call this experiment 1 is flipping a coin twice. That is, flip a coin 2 times, and then the interesting outcome or interesting output or result is basically observe the side of the coin that faces up, that is either heads or tails. That is the outcome of this experiment. Next one, another example is toss a couple of dice and count the numbers or note the numbers that are on the side facing up. That is, this is the outcome. That is, the noting the numbers on the 2 dice is the outcome, and tossing the dice is the experiment. Sample space. So for experiment 1, that is flipping a coin twice, the set of all possible outcomes includes heads and tails, tails and heads, tails and tails. So this is the set of all possible outcomes. There is no other possible outcome includes either heads or tails. And from experiment 2, the sample space consists of basically ordered pairs of 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, and so on up to 6, 1, 6, 2, and to 6, 6. So this is a very large list basically. It consists of 6 times 6, that is 36 outcomes. So as the size of the experiment or as the number of outcomes of an experiment become larger and larger, it is difficult to list them as a set. So we can also define a sample space by using rules. For example, the set of all possible outcomes, that is a sample space from experiment 2, can also be defined as an ordered pair x, y, where x, y belongs to the set of natural numbers and x and y are always less than the number 7. So this property is always satisfied by the elements of this set. That is 1, 1 to 6, 6. They always satisfy this property. So this is another way of defining the sample space. Now look at some examples on events and event spaces. So for example, from experiment 1, we can define an event as consisting of only one head. There are 2 possible events for this. There are 2 possible outcomes for this event or in this event, that is heads and tails or tails and heads. And in the experiment 1, we can also define an event T1 that has, for example, as at least 1 tails. That is, this event consists of 3 possible outcomes. That is heads and tails, tails and tails, tails and heads. So there is at least 1 tails in each of the outcome. And event space, for an example for event space, can be the set of all the events that has I heads. That is, for H0 there are no heads. That is, the possible outcome is TT, that is tails and tails, and similarly H1 and H2. So note that the event space H is a collection of all the events, that is H0, H1, H2. And the sample space is a collection of all outcomes, that is H, heads and heads, heads and tails, tails and tail, heads, and so on. So the major difference between sample space and event space is that the elements of the sample space are outcomes. The elements of event space are events. Basically, event space is a set consisting of sets of outcomes, which are events. So in other words, each event is a subset of the sample space. But but this same event is a element of the event space. So that is the difference between sample space and event space. Now let us look at the fundamental axioms in probability theory. So for any event A, as defined previously, the probability of this event A is always non-negative. That is, it is either 0 or a positive value. And next, the next axiom is the total probability is always 1. That is, the probability of the total sample space is always 1. And then the final axiom is, for mutually exclusive events, that is, their intersection is empty set, the probability of the union of these exclusive events is always is the sum of the individual probabilities. That is, for example, if A1, A2, A3 are mutually exclusive events, then the probability of their union, that is A1 union A2 and so on, is equal to the sum of probability of A1 plus probability of A2 and so on. So let us look at an example illustrating these axioms. So now consider this experiment 1 we discussed previously. Now we have the event space H, which has the events H0, H1, H2, where H0 is the event with the outcomes tails and tails, and the H1, that is event with only one heads, that is heads and tails, tails and heads, and so on. So in this case, when the event A is equal to either H0 or H2, then the probability of A is obviously 1 by 4. And similarly, for when event is equal to event A is H1, that is the event of interest is H1, then the probability of A is 1 by 2. And finally, for event A is equal to empty set, that is when there is no observation, then probability of A is 0. So this is basically illustrating the first axiom, that is probability of an event is always non-negative. That it is 0 for the empty set A, that is when the event A has no observation, that is no outcome, and when event A has some observation, then its probability is always positive. And for the sample space S, which consists of all the possible outcomes, in this case all the 4 possible outcomes, then we can clearly see that, and thus the probability of the sample space is always going to be equal to 1. And actually it follows from the definition of probability itself. That is, probability is a frequency of a particular event as compared to the total number of events or total number of outcomes. For the total sample space, then both the numerator and denominator have the same number of counts. That is why the probability of sample space is always 1. And then mutually exclusive events. Consider the mutually exclusive events H0, H1, H2. Then we can clearly see that the event space H is the union of these exclusive events. Hence, the probability of this event space is equal to the sum of the probabilities of these individual events, which are mutually exclusive. Thus, in this example, we can see that the probability of the event space is equal to the probability of sample space, that is 1. And it can be easily seen as the sum of probabilities of individual events. Let us look at some theorems that are either direct consequences of the axioms from previous slide, or either related to those axioms. So let's look at theorem 1. If you have a set B, that is a union of m events, that is m sets, and each of these individual sets are disjoint from each other, that is they are mutually exclusive, that is their intersection is equal to empty set, then the probability of the event space, that is B, is equal to the sum of the probabilities of individual events. So the probability of the event space B is equal to the sum of the probabilities of the individual events Bm. So an example of this theorem is already seen in the previous slide, where the probability of the event space H is equal to the sum of the probabilities of H0, H1 and H2. And theorem 2 is that probability of a sample space is sum of the probabilities of the outcomes. That is, if a sample space S has n samples or n outcomes, then the total probability of the sample space P of S is equal to the sum of the probabilities of the individual outcomes. And finally, in a sample space S with n outcomes, if each outcome is considered equally likely, then the probability of each outcome is nothing but 1 by number of outcomes, that is 1 by n. So, and let us look at some of the consequences of these theorems and also the axioms we learned from previous slides. The probability of an empty set, is always 0 because there is no observations, and hence the numerator in the definition of probability is always 0, and hence the probability itself is 0. And the probability of a complement of an event A is 1 minus probability of the event A. This theorem or this result can be easily derived from the axiom 2 or event A, and I will look at an example of event A in the next slide. For any events A and B, the probability of the union between A and B, that is probability of A union B, is always equal to the sum of the probabilities minus probability of the intersection. And finally, if an event A is a subset of event B, then the probability of A is always less than or equal to the probability of B, because A is contained within B. So the total probability of B should always be greater than or equal to probability of A. So let us look at some examples that illustrate these ideas. Now let us look at some examples illustrating these theorems and axioms. So for the probability of the sample space is equal to the sum of the probabilities of the individual outcomes. So consider the experiment 1 from previous slides, where we have tossed a coin twice and note the outcomes. So the total number of possible outcomes is always 4 in this case. So the probability of the sample space S is equal to sum of the probabilities of the individual outcomes, which is 1 by 4 for each of the outcomes. So the total probability is 4 times 1 by 4, which is equal to 1. Now consider another experiment where you toss a single die with 6 spaces and note the outcome. So the total number of possible outcomes is 6. So the sample space has the numbers 1 to 6. Assuming that it is an unbiased die, we can say that each of the outcomes are equally likely. Then the probability of each outcome is basically 1 by the total number of outcomes, which is 6. So the probability of Fn is 1 by 6. Next, let's look at probability of a complement set. So define an event D that has only heads in the second toss. Then the possible outcomes are heads and heads, tails and heads. We are talking about experiment 1 here. The event D is defined as two outcomes, or consists of two outcomes, heads and heads, tails and heads. The outcome heads and heads and tails, and the outcome tails and heads. So the complement event is basically the other side, that is where we have only tails in the second toss. That is D complement is equal to heads and tails and tails and tails. So the probability of the event D is obviously 1 by 2. And then the probability of D complement can be defined as 1 minus probability of the event D. That is 1 minus P of D, which is equal to 1 minus 1 by 2. That's equal to 1 by 2. Now let us look at an example for the theorem, that is the probability of A union B. So let us define two events A and B. So A can be defined as all outcomes that has at least one heads in the pair. That is there are three possible outcomes. That is heads and heads, heads and tails, tails and heads. And let us define B as having outcomes that have at least one tails. That is heads and tails, tails and heads, and tails and tails. So the probabilities of both the events are equal to 3 by 4. And the intersection of these two events is basically the outcomes that have only one tails and one heads. That is tails and heads, heads and tails. So the intersection has a probability, that is probability of intersection is of this intersection event is 1 by 2. So now we can easily calculate the probability of the union, that is A union B, which is basically, here the probability of A union B can be easily calculated. First we note that the set or the event A union B is nothing but the sample space S, because it contains all the possible outcomes, and the probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B from this theorem. So the solution is probability of A union B is equal to 3 by 4 plus 3 by 4 minus 1 by 2, that is equal to 1. And let us look at an example on probabilities of a subset compared to its superset. So let us now we have already defined two events D and A. So we can clearly see that the event D is a subset of event A, because heads and heads, tails and heads are already there in the event A. So obviously D is a subset of A, which implies that the probability of D, which is equal to 1 by 2, is always less than probability of A, which is equal to 3 by 4.